Very interesting.
All right, everyone, welcome. We are going to get started with a panel now to conclude our afternoon on data-centric compute. We've got 4 panelists along with myself. My name is Jason Molgard. I'm a Principal Storage Solutions Architect at Solidigm. I'll be the moderator. We have Gary Greider, who's a Senior Director for Computing Technologies at Los Alamos National Labs. He is on an urgent phone call, so he'll be joining us in a moment. We have Anupam Thakur, who is a Director of Strategic Planning and Architecture from Microsoft Azure. So welcome. We have Pankaj Mehra, who's a research professor and computer scientist, research professor of computer science at The Ohio State University, and also a CEO of Elephant's Memory. And last but certainly not least, we have Nader Salessi, who's a storage executive and a computational storage veteran, as he calls himself. But he actually is being humble. He's a very experienced expert in computational storage, currently working with MaxLinear. All right, so we have an opening question to get the conversation started. And then after that, after each speaker has an opportunity to give their answer to the question, then we'll open it up to the audience questions. So be thinking of some questions that you'd like to ask our panelists. So our opening question is, what is the past, present, and future of data-centric compute or near data compute? So Gary was going to go first, but we'll go ahead and skip him for now, and we'll come back as soon as he's available to join us. So Anupam, that puts you up first.
Yeah, thank you everyone for joining us today. I wanted to just talk a little bit about the landscape of models and this concept of memory wall. So as we all know, models are very memory intensive. They are growing exponentially in the number of parameters that are being deployed per model. And this creates this phenomenon of memory wall where your parameters are growing exponentially, but the memory bandwidth hasn't kept up. And it's doubling roughly every 2-3 years. But you see the transformer size has gone 240x in those 2 years. So what researchers are doing are looking at techniques like quantization, where you train the model in wider data types like FP16, FP32, but you quantize it down to FP4 for inference without losing much efficiency and accuracy there. There is flash attention, grouped query attention, where you are bringing less of the KV cache heads, and instead you are using pre-learned values that still provides pretty good result. So that way you reduce the memory pressure, the traffic that's on the memory interface. So with this, as model scale and the context lengths grow with the agentic AI, agents that are working autonomously, they may build a long context over time as they are executing the task you have given them. So the memory bandwidth, despite some of these improvements, will continue to be challenged and will face the same problems that we have faced over the past couple of years. So yeah, I'll turn it back to you.
Great, thank you. So Pankaj, I believe you're up.
Yeah. So I think if you go over the presentations of today, it's very clear that there is a certain direction to the evolution of computational storage. But the idea of computational storage actually goes back quite a few years. Even the first implementations predate even flash memory and were done, for example, with hard disk drives and systems from IBM and Tandem in the database world. In the mid-90s, there were fully shipped out implementations to customers like NASDAQ and America Online in those days. They were big companies. So that was before NVMe and the great work Jason and team did in SNIA to standardize computational storage APIs for flash, building upon the learnings of the old, but also injecting new ideas that were more favorable to the NVMe transport. And I think, if you look at the italicized text at the bottom left of the slide, it says storage first architecture. when the only offload, standardized offload availability was on storage, we naturally adopted the most prevalent storage protocol, which was NVMe, and tried to put accelerators on NVMe. As Gary explained to you, that actually was quite fruitful. But if you look at some of the challenges that we faced getting that kind of computational storage to market, the problem was that if you were, say, SQL Server database team, and some of your data, some of the time was in storage tier, and some of the time was in buffer cache in DRAM, you didn't want two different interfaces to computational memory and computational storage depending on where that piece of data was. So as we got to some commercial grade efforts with customers like Zoom, Microsoft, IBM, and some of the other companies, even some Department of Energy labs on cybersecurity efforts, we realized after going a long way that we cannot have a fragmented world where each vendor, each type of accelerator, and each location of accelerator presents a different API in a different generation. That causes a lot of wasted effort. So that brings us to current year and the past few years. What the thinking has been is that we should move to an accelerator first architecture around CXL. So CXL itself kicked off around 2017 for standardization work. As it matured and it became clear there were going to be type 2 devices, we realized that for accelerator standardization, we should talk to the accelerator from GPU or CPU, which is going to offload, as a brother, and memory behind the accelerator, not memory in front of the accelerator. Okay? These learnings have been with us. CXL has now given way to UA-Link on GPUs. AI workload has changed the equation during these years. So that brings us to where this is going next. And where this is going next is, you heard some of the speakers describe how important it is to embrace open formats from Apache. Like, Gary's work used Parquet for the stored data, but then when it was entering data in flight and in-memory data, we go to Arrow. Okay? So what are some of the formats that Gaurav and I talked about, right, from top-down point of view? JAX and TensorFlow, these are the high-level formats, and then we are compiling them down. So if you look at the list of things that are listed there, we are moving to what Gaurav very well explained in his presentation, so I don't need to repeat. We are moving to a world of data-centric architecture, and this is my view of where things have been and where they're going. I'd love to talk to you guys about it.
Thank you, Pankaj. Nader.
Okay. Thank you, everybody, for joining us. So in the past, as we have seen, all the resources that was needed was being deployed. You compute different categories of compute, memory, storage. But nowadays, we are facing a challenge. One is energy. Availability of energy, energy consumption is a big challenge for the whole industry. Availability of higher bandwidth or high HP memory, high density memories, and high density capacity also is a challenge, especially with the current market condition availability of the storage. So a few ideas for providing a remedy for these type of challenges. One is by deploying the compression engine or hardware accelerator that has the computation built into it in the SoC for compression, dedupe, hashing, or encryption. First, you can expand your storage capacity by 4x, at least nowadays, as you can see on the graph on the top. Secondly, by deploying the hardware accelerators, we have implemented and tested, and we have incorporated into the new TCO model, the time to completion model. It shows that hardware accelerator completes the workload in a much shorter period of time compared to the software running on the general purpose compute at lower power consumption. And it saves more than 90% on the energy consumption, the critical part. Thirdly, as you can see on the graph below, it's a better use of resources, better utilization of the resources. Instead of using the CPUs for doing the workload, the hardware accelerator accelerates it, and additional resources become available for your other applications, while, again, you're saving the energy consumption. And what we see coming in the future, obviously moving compute closer to the data, but more importantly, to be the data-centric, meaning to have more devices with inner storage hardware accelerators built in.
Thank you, Nader. Gary, I'll go back to your slide.
Okay.
I'd like to see the-
Uh,
or you can
I
see.
can see it. So I was asked to, do a look at past and current and hopefully near future views on data center computing. And since I'm probably the oldest, my past probably is going to go way back. But just wanted to mention how, a lot of this stuff is not new. Data parallel and small word vector and all that kind of stuff. We had that in thinking machine systems in the late 1980s and early 1990s. The first top 500 list on the first top 500 list on the top machine on that list was a CM5 at Lanel, and its baby cousin was 64,000 1-bit wide processors, 1-bit wide, and you could have any size word you'd like, from 1 bit to however many out to 64,000. And so variable length floating point is not new. And CUDA isn't the first time we did data parallel languages. I'm sick and tired of hearing that Ian Buck invented it. I like Ian, great guy, but he didn't invent it. It was invented a long damn time ago. I remember the first supercomputing. In 1986, we had a little committee, and we were talking about C star and data parallel Fortran. This is not new either. And even before that, Los Alamos had a language that was trying to take integrals written by mathematicians and convert them into code, and that was called MadCap. That's not even new either. So all this stuff is, we can study the past, and we should. So that's my past story. The current story is, it's dominated by what you've heard about today, right? A lot of GPUs and TPUs and NVLink and CXL and all the things that you've heard about. And I already talked about Apache pushdown, so don't need to talk about that anymore. And then hopefully the near future is to get to the point where what we used to do in DOE and DOD with specialized machines that we spend ungodly amounts of money on, SGI origins and HPE superdomes and all those things that gave us essentially data-centric computing, the memory first, and it's all around the memory, or even custom architectures that had all-to-all networks, and had thread storm processors for keeping thread lookups going across all the network links at the same time to try to be memory-centric. Hopefully we get all that stuff in commodity form. The only way we're ever going to get good at this is if everybody can use it, and not just weirdo sites like NSA and LANL. And so it's got to become ubiquitous, or it's not going to work for everybody. And so we've got to get there. And so I think OCP is a grand way to help get there, right, by standardizing how we get this stuff done, or at least pseudo-standardizing it, and getting it into commodity forms like CXL and use of file system technology like FAMFS or object or however you want to provide the virtual address space. There shouldn't be 19 ways. There ought to be 1 or 2, and that's it. That's all you need. And other standardization techniques, and you've got whole communities like the Apache ecosystem that are doing stuff like this. Don't leave them behind. Let them be snowflakes, but just figure out how to map them in, so everybody gets on the same page. And if we can make this to the point to where, I don't know how many times we've said memory-centric computing is going to come, and it comes and then it goes away, and then it comes and it goes away again. the only way it'll stay forever if it makes it into our hearts and minds, everybody's, right? And so it's got to be standardized. It's got to be in the hands of a common man. You've got to be able to get it on a Linux CD. You've got to be able, well, I guess you don't use CDs anymore, do we? Right, I mean, my point is it's got to be ubiquitous or it will go away again, and we don't need that.
Thank you, Gary. That's great. Does anyone in the audience want to ask a question?
So how do we achieve that? That's my question. Let me give some background. Recently Jason has spent tremendous effort developing a computational storage standard within SNIA.
Mm-hmm.
And I don't know really where that has gone. I'm sad that it hasn't taken off. And you all talk about the need for it. Maybe Pankaj, you maybe said that was maybe NVMe based, maybe not, technically not NVMe based, but maybe not the right thing. But how do we get there? Do we need to restart it? How do we make the standard development faster? Because I think in many ways, and I did participate with Jason, so we move it somewhat of a glacial speed. It means that whenever the standard comes out, it may be too late. I don't know, but yeah. I want to get some perspective. Can we get to a standard for near data computing?
Yeah, let me take a quick stab at it, and there's more knowledge around me, so I'll keep it short. I think successful standards in hardware work differently from successful standards in software. In software, you have to codify best practices. In hardware, you do enabling standards, so you have to do standards where two things don't know how to talk to each other. Okay? So in software world, you can be a bit back-end loaded on your standardization work, waiting for good ideas and good stacks to evolve in their own way. We have 40 years of push-down optimization in relational algebra, multiple generations of optimizers, two of very influential open ones like Git's Grapher's work at Wisconsin that gave us A-stars type optimizers for SQL, and Calcite, which was used almost everywhere in the industry for distributed and for offload. We don't have equivalent maturity in linear algebra optimization. So when we do the kind of devices, the variety we saw in PNM, PIM, near storage, near memory compute, etc., we will need to take what the user wants and rewrite that in the way of the device. And that layers, like Gaurav showed, are evolving starting from AI workload like neural networks, and then coming through multi-level IRs to the back end. We don't know today if PJRT plugin is a performant architecture. We know it is a portable architecture. So part of what I see to get there are a few gaps that we need to address. One is linear algebra optimizers that are open and build upon, integer, modular arithmetic, and other things that we used to use in compilers. Number two is open formats for graph data and sparse data, which are missing from Apache standards like Arrow Compute and Arrow Data. And then take the level of operations that are available in Arrow Compute above dot products and matrix vector products to sparse matrix vector, sparse matrix, and gem, other higher level operations that are needed, minimal level. So I think these are some of the things that we need to do.
Anyone else want to take it?
I like SQL algebra, and I like the fact that you can have one graph that everybody understands. That certainly is a key to success. Another key to success, I think, is allowing for snowflakeism. The Apache ecosystem got this right. They allow snowflakes. They just have minor things that they agree on that you can write a very small amount of code and plug into a whole ecosystem, but yet you still get to be your unique little software self and write your own little fun thing, right? And do the best thing for your company or your ego or whatever it is you're writing your code for. And so whatever we do, we need to allow for that in the software space. So don't overspecify it. Bet on something simple like algebra or something that's immutable in a way, or a graph that we can all agree on, or at least a way to think about a graph that we all agree on. I think those are the keys to success, is find just the smallest amount of stuff to agree on and allow snowflakeism to occur, because it will, whether we like it or not.
I'll just like to add that there wouldn't be a better time to show improvement from offloading or in-memory processing, because as whole inferences and training workloads, they are using a lot of capacity, and if we can improve that in any way, improve user experience, you will see adoption really quickly.
But the ship has sailed on a lot of things. Like, for example, threading models. You could go use, there's been, 9 wars about threading over the last, I don't know how long, OpenCL and OpenACC and Open whatever the next 15 acronyms are. And so we've got to admit that some ships have sailed already, right? And pick our battles carefully to find things in that space we all agree on.
And some more comment that for the hardware, as you mentioned, SNIA has come a long way to define computational storage. And still, there is a long way to go, but we need to continue to focus and continue collaborate collectively as an industry around that. And in the meantime, use whatever is open standard, open, let's say ZFS, for example, really run on with the hardware accelerator to be optimized to be deployed while continuing on the standardization of it.
I think one of the things that I see is that to have common standards for memory and storage offload, we will have to think about what we like about memoriness, and what we like about storageness.
Yeah.
Okay? If you go back to, we were discussing in CMS team today, if you look at failure mode of disaggregated memory, it behaves more like non-volatile and persistent memory in that way. It is decoupled from failure of a lot of CPU things and GPU things. Okay? So it is naturally non-volatile in its, or naturally persistent in its architecture, okay, in that way. The second thing is that memory things, because they have been in an addressed architecture in the CPU world, they don't have good naming architectures. The only naming architecture is in things like Python or language runtimes. By the time you come to memory management system, it hasn't a clue what something is called. And so if it's going to last a long time, after the computation goes away or the guest OS dies or something, the memory management guys don't have a clue what to call it. So if you want to shift to a data-centric architecture, you have to think about how will we move from this addressing-based paradigm to a declare and use paradigm. You just find data and start using it when you fire up a new compute. There is nothing like that that's there for AWS Lambda today. Okay? So partly, I think that we sometimes think about, well, Gary talked about computational storage. What has that got to do with CXL? Well, he also talked about file systems, and file systems provide a naming service that we all love to hate. Right? POSIX is the most loved and most hated thing at the same time. So part of it is, how will we combine good ideas from memory and storage and take things that have worked for computational memory and computational storage and give them a uniform feel to developers with the goodness of memory and storage combined. And I think that slower initiator target protocols like NVMe have a place in that ecosystem maths, like your question was, in that they are very useful for bulk data movement. Okay? So when we have move, copy, share verbs, we will want to build on some of the goodness of the SNIA standards like SDXI and the NVMe technical group work. And then for some of the stuff that is more like pipelines of HPC or AI, we will want to embrace the metaphor of compute memory world. So that is, that takes a little bit of abstract work, more computer science thinking and less electrical engineering thinking, in my opinion. So I think that's how we will get there.
Great. Did you have one to add something?
Yeah, just another comment. The word of the memory and storage, eventually it becomes two different things when it goes into the data-centric, mainly because of the amount of the storage or amount of the data that resides on the memory versus amount of data that exists or is going to reside inside of the mass storage. And those are also have two different gravity that we need to see what's the best way of incorporating it.
Right.
All right, well, I wish we had more time. Any parting thoughts that anyone wants to share before we close today?
The only other thing, it's, again, energy consumption is a challenge, whatever we do, be it memory-centric, be it storage-centric, or compute-centric. So we need to keep thinking about what workload we are dealing with and how can we take advantage of accelerating it and reduce the energy consumption, because we are all facing that challenge.
I spent some time with Ivan Sutherland a few years back. Interesting guy, right? And he chewed me out over and over again for letting the world be consumed by way too many synchronized clocks inside of silicon. And have to agree with him, right? There's a lot of them. And he suggested that as I get older, I should find something like that I should be harping on. And I guess the one that I can think of that is would be interesting, I think, for this discussion, and that is, had we not given up on count key data and said no to blocks, would we even be here right now? Does anybody remember what count key data is? It's the way storage systems used to work. You didn't get a block, you got an offset in the length. And it was asynchronous, and you sent a program to the disk controller to say, walk this tree for me and give me the answer. That's the way disk drive started out. And we gave up.
Oh my God.
Sounds like you're talking about data flow.
In many ways.
Oh my God.
I am just looking forward to the outcome of this work stream and how it helps latency, how it improves some of the bottlenecks that we face for AI workloads. And yeah, I'm super enthusiastic and optimistic about what we will accomplish here. So yeah, thank you for having me.
Absolutely.
Yeah.
Pankaj, anything else?
I will just say that if you're sitting in this room and there are ideas that you wish we had talked about, just come to our weekly meetings and contribute them, and I hope you will come and stay.
Yep.
Agreed. Agreed. Well, thank you, everyone. Let's thank our panelists for joining us today. Thank you.